Okay, no, it's okay.
Okay, great. No one missed anything. So, okay, so I'll start off by describing the problem, which is we want to compare free and interacting SPTs in the specific case of the bot spiral studied by Krulewski. And I'll start off by saying, how well can we see this using invertible field theories, maybe as a test of our ansatz there, and then what new things do we learn by trying to model this situation. So start off with the problem. So as probably this audience is pretty familiar, when we talk about SPTs in terms of Hamiltonians and lattice models, we usually start with some space of Hamiltonians that all have to satisfy a prescribed symmetry. And then we say, let's take out the gapless Hamiltonians. We only want to look at gapped Hamiltonians and with those symmetries. And then we'll call a phase a connected component of what we have left. And so then two Hamiltonians are in the same phase if they are connected by an adiabatic path that goes through symmetric Hamiltonians. If we're talking about fermionic SPTs, we can also look at the special case of free fermion phases, where if we're looking at a second quantized Hamiltonian, it will only have quadratic terms, so only hopping or pair creation and annihilation terms. And these are nice models because they're exactly solvable, and they're a subset. But we can look at free Hamiltonians modulo free deformations and see what phase classification we get. And we can compare this with the interacting side, and they won't always be the same. And so we would like to know when they differ. So I think one of, if not the first example of a fermionic phase that had different classification on the free side versus the interacting side was the time reversal symmetric Majorana chain, as shown by Krulewski. So let's start off with the Majorana chain. So we have these sites. Each site has two Majoranas. The non-trivial phase of this model connects the Majoranas on different sites to each other. And the Hamiltonian looks something like this. So I can stack this non-trivial phase as many times as I want, and I cannot trivialize it using free fermion terms. So if we didn't have the time reversal symmetry, we could add a term like this on a finite wire, and that would reduce us to a Z mod 2 for the normal Majorana chain. But if we have to preserve this time reversal symmetry, we cannot add that term, and there isn't another term you can add to trivialize it. So the phase classification we get is a Z, which is just an integer counting how many wires we stacked in this non-trivial phase. Okay. So that's the free fermion view on this model, but we can also look at allowing interactions in this model. So if we stack some copies here, what Krulewski showed is they came up with an explicit interacting term, which I've only written part of on the bottom here. And with this quartic interaction term, so it's not free fermion, it's quartic order, you can trivialize 8 copies of this phase. So now instead of a Z, we get a Z mod 8. So class BD1 would just be the type of symmetry with this time reversal that's squaring to 1. So once this example was worked out, you could ask, what happens for other types of symmetries? What about other symmetries, other dimensions in the tenfold way, maybe beyond? When do we see everything with free fermions? When do we not? And the example we wanted to look at was this bot spiral. I don't think they use this word necessarily. I think maybe Ryan Thorngren coined this term, but it was studied by Krulewski, and they were looking at a sort of a mild generalization of the tenfold way. So let me just recall, let's consider the tenfold way and only the real types. So let's look at the eightfold way. We have these different symmetry types. You start off with this laser pointer or something. We start off with maybe no additional symmetry, and then we have class BD1 with that time reversal. We can have time reversal squaring to fermion parity. And these symmetry integrators generate a Clifford algebra type symmetry for us. And so we can label each of these with a Clifford algebra, or just with an index S that tells me which Clifford algebra I'm in. And in addition to being 8 periodic from that kind of bot periodicity, it's also 1,1 periodic. If we are classifying our free fermion phases in terms of a K-theory group in degree D plus S minus 2, this is the same group if we increment D and decrement S. Oh, so now those two things are multiplied, so that's a typo, so it should be a plus sign right there. Sorry about that. I was fixing a different typo and introduced a new one, but these are the same. Okay, so there's this 1,1 periodicity. And what Krulewski and Stern found was that on the interacting side, it's much more interesting. So it sufficed for them to use quartic interaction terms again, and they were able to, via dimensional reduction approach, classify the interacting phases connected to certain free fermion models here. And so instead of being 8 periodic, instead of being 1,1 periodic, as they went around, they saw higher and higher orders of 2 in the classification. So every other step, basically, there was a multiplication by 2 in the number of phases they could see. So for example, here's that time reverse symmetric Majorana chain. So in class BD1 in dimension 1, that was a Z classification. And on the right-hand side, it's mapping to that 8 in parentheses, that Z mod 8. Kind of depends where you start, whether you start at the Z mod 8 or Z mod 4. But as you go around, it's not periodic anymore. We get this multiplication by 16. So we wanted to recover this using homotopy theory. Yeah. So there's like 2 sets of numbers in this figure, which is taken from Krulewski and Stern. Yeah, sorry. So that's the order of the classification of interacting Hamiltonians connected to a given free fermion Hamiltonian. So you take, for example, the time reverse symmetric Majorana chain, some free fermion Hamiltonian, and then you say, let me consider this Hamiltonian, but now allow me to add interaction terms to it. Then this number says how many copies of that free fermion non-trivial phase do I have to add to trivialize it with interacting terms, with higher order interactions. Thanks for the questions. Yeah.
Yeah, for the interacting system, whether this fractal system has some conditions, I mean, starts by certain symmetry or not.
Yes.
General composition, I think, is very complicated.
Yeah, so they have to satisfy certain symmetries. The ones we're looking here are basically the tenfold way symmetries, and then I'll say a bit more later about prime versions thereof. But yeah, like time reversal particle number type conservation symmetries. We're not really looking at spatial symmetries here, although there's a bit of caveat there. Yeah, thanks. Yes.
Stable tree equals number.
Sorry, can you say that again?
Spiral.
Yes.
Right.
So they're saying if this is from that paper, and so if you start at dimension 1 and you have a Z mod 4 classification and you perform some dimensional reduction procedure, except it's actually maybe dimensional like accretion, it goes up in dimension. Then you get to dimension 2, the classification is still a Z mod 4 with the free fermion model you get from that. But if you dimensionally increase again, it multiplies by 2, you get a Z mod 8. Was that your question?
Well, what about the equal people conducting the summer here?
So no, I don't think that's in this spiral. We're looking at, let's see. So instead we'll be looking at something called the D prime superconductor, which would be related, but I don't think the P plus IP shows up here. I would say like P plus IP would be class D, right? So I guess you could say no symmetry, but I would still consider that to be an SPT in what I was saying earlier. But class D, well, class D prime is in the spiral, and I'll say more about what that means later. Yeah, thanks for the question. Maybe in the interest of time, I'll try to come back to that and see. Yeah, right. So we're always starting where the free fermion classification is an integer. Sorry, I didn't say that. So we did also compute what happens if you start with the Z mod 2. Nothing to compute when you start with the 0. So, but the most interesting case is when you start with an integer classification on the free side. And so this is saying when you start with an integer classification, that's why I chose the dimensions in the way I did. Then it's reduced down to a Z mod 2 to the n for some n. Yeah, thanks for the clarification. Okay, so we wanted to model this instead of trying to think about moduli spaces, which aren't super well defined for us. We didn't quite know how to work with that. We instead wanted to use the ansatz that we can describe these systems using invertible field theories. So we're going to follow Fried-Hopkins formulation of this to model the passage from your free fermion to your interacting fermion Hamiltonian as a map and homotopy theory. So the source is going to be free fermion, SPTs. This will be some kind of K-theory group, maybe twisted equivariant, although we won't necessarily see that today. And the target will be described by invertible field theories up to deformation, and I'll say more about that in a moment. And so this map is interesting when it's not an isomorphism. So sometimes it'll have a kernel, like the 8 copies of that time reversed symmetric Majorana chain might, so you can also study the image. So these are the interacting models connected to free fermion Hamiltonians. Could also have a co-kernel with intrinsically interacting SPTs. We're not going to study that today for our example. So today we're going to look at this F2I or free to interacting map for the case of the bot spiral. And we're going to study its image because that's what Krulewski and Stern did. They said, let me take a free fermion and see what happens to it. They weren't looking at the intrinsically interacting models there. So that's our goal. So let's see how well can we recover what Krulewski and Stern did by physical methods using homotopy theory. So spoiler alert, just in case I run out of time. We were able to compute some things, and we'll come back to this later, but we were able to define a map. F2I, it goes from some K-theory group, the L and K degrees I'll explain later. And this is a group of invertible field theories with manifolds of some kind of twisted spin structure. We were able to compute its image, and we'll come back to this at the end, hopefully. But we see those factors of 2 to the n in the interacting classification. And then in the third case here, this is when we start with the Z mod 2 instead of starting with the Z classification. So this last case isn't quite so interesting. So my goal will be to come back to this and explain it a bit better later. But one takeaway is that we are able to recover their results, which is exciting. However, it wasn't, I don't know, we had to make some choices along the way in how we were modeling this, and these kind of subtleties in making things compatible with dimensional reduction and subtleties in our choice of how to model the symmetries ended up being kind of interesting. And so time permitting, I'll discuss that. But okay, so this is result. We'll come back to this. Now let me say a little bit of background. So there's many, many ways to phrase the tenfold way of free fermions. I'll just say one way that we used. So we want to consider a finite dimensional superalgebra, and we want to take the K-theory of this algebra. We can compute the K-theory of this algebra by looking at projective modules over the algebra that admit the action of some Clifford generators. If we're looking in degree n, we want to have n negative Clifford generators, and then we mod out by those that extend to the action of 1 or. I'm going to stop trying to use the laser pointer. And so the ansatz is in spatial dimension D. We'll say free SVTs with A-type symmetry are going to be classified by this K-theory group, but we have this usual shift by 2. And then it's due to the degree, like the homological degree, it's in negative D. But you can recover the tenfold way in this framework. We just take A to be one of the 10 superdivision algebras, one of the 10 Clifford algebras. So in particular, if we look at class ED1, that time reversal symmetry gives us the generator of Clifford plus 1, and then the K-theory group you get for dimension 1, for spatial dimension 1, is AZ. So that's going to be the running example here. So that's the K-theory side of things, and I want to say a little bit more about the interacting side. So to gear up for talking about the interacting side, let me just recall the definition of a stable tangential structure. So a stable tangential structure is the data of some map X to BO, the classifying space of the orthogonal group, and the structure on a manifold M is a lift of the classifying map of a stable tangent bundle of M through that map X to BO. So for example, if I look at SO, including into O, this recovers an orientation for me. You can also look at spin structures, which we'll be using today, and unoriented versions of spin structures like pin plus and pin minus will be really important examples for us. So we can ask for these tangential structures on our manifolds to encode the symmetry type of our theory. Then what do we actually compute? So let me recall the Bordism group So the Bordism group of d-dimensional manifolds with some kind of tangential structure C is going to be generated by closed d-dimensional manifolds equipped with such a structure, modulo Bordism as an equivalence relation. And then the group operation is disjoint union. So for example, I could take circles or oriented one manifolds and disjoint unions thereof. And then Bordism tells me that two of them are equivalent if I have a higher dimensional manifold who can relate them on the boundary. So for the running example related to the Majorana chain, let's look at dimension 2 and let's look at pin minus structures, which are related to pin structures. In this case, the Bordism group is a Z mod 8 and it's generated by the real projective plane with a choice, with the appropriate choice of pin minus structure. I claim this is the same Z mod 8 as the time reversal symmetric Majorana chain from earlier. And then let me just jump through a couple hoops to connect that back up. So we're going to, on the interacting side here, we want to use invertible field theories. Let me just start by recalling TQFT. So usually we talk about this as a symmetric monoidal functor from a Bordism category to a Bordism category, something very categorical. But if we're looking at invertible theories, these have a universal target, the Anderson dual to the sphere. We won't need too much about this today, but this is a spectrum. And if we use the classification proven by Friedrich-Hopkins with a little more adjectives here describing the situation, we can then classify our invertible field theories of interest. So if we want to classify fully extended reflection positive D+1 dimensional invertible field theories up to deformation, this is some group that you can compute. And I'm going to just write an upside down omega for it. So omega for Bordism, and then it's upside down because it's dualized. And yes. And from the universal property of the Anderson dual, we get an exact sequence here. So the middle is the group that we care about, and then these groups on the side are Bordism groups. So the group that we care about can be computed from Bordism groups in a couple of dimensions. Okay. So this is what we're going to use about invertible field theories here. And so they're closely related to Bordism groups, and for the rest of the talk, I'll mostly be talking from the Bordism perspective. So those were some background, that was some background on each of the classifications, but we really need to connect them. We want to produce a map between them. So we need something that will compare twisted K-theory and invertible field theories, but before we even do that, we probably need to know how to match up the symmetry type. So, you know, what symmetry group, what tangential structure should be used, like which things correspond to each other. So I'll address that first. So the way we're going to use this is to use fermionic groups. So a fermionic group is some topological group, GB, the bosonic group. Then an extension of this by Z2, which tells you how fermion parity acts. This will give you a class in H2 of BGB. Then there's also a grading. So it's a Z2 graded algebra. And this grading tells you whether your symmetry is acting unitarily or anti-unitarily, whether it reverses time or not. And so using these groups, you can recover the tenfold way and other symmetry types you might be interested in. And yeah, so it comes down to having this group GB and then these two homology classes, roughly speaking. And yeah, this is not including the most general type of like Friedmore group, for example, but this suffices for our purposes today. And so what's great about fermionic groups is that they work really well for both sides of our story. So if we start off with this fermionic group encoding our symmetry, there's at least two things we can do with it. So one thing we can do with it is we can form the fermionic group superalgebra. So we take the normal group algebra of the extension GF, and then we identify fermion parity with -1. Another thing we can do is we can form a stable tangential structure out of this fermionic group. So we can form this as a pullback, where we take the data of theta and omega coming from the fermionic group to give us the map on the bottom. You take a standard map on the right-hand side, then we just form that pullback to define this tangential structure H of GF.
Bottom, you don't want field, right? You want some kind of minimum train space.
Oh, sorry, yeah, that's a typo. Yeah, I want BZ2 cross B squared Z2. Sorry. That's an important point. Thank you for pointing that out. That's what I get for redoing my slide. Okay. So hopefully, if anyone's confused about that, they can ask later, but that's totally right. Okay. So modulo that mistake, we can then do two things with these data. So we can, on the left-hand side, take the K-theory of that superalgebra that we formed. This classifies some kind of free SPTs that we're interested in. And on the stable tangential structure side, assuming that we fix that BO, we can then get tangential structure, plug it into the theorem of Freed-Hopkins, and compute these invertible field theories on manifolds with that tangential structure. So now we have, starting from some fermionic group that tells us the symmetry, we have a way of talking both about the free side and about the interacting side. Okay. So let me do an example here. So if our fermionic group is just a Z2, our bosonic group is just a Z2, and then we take the non-trivial first cohomology class here, so X, and then the trivial second cohomology class. X will be the class of the bundle sigma over BZ2, so the tautological line bundle associated to the sign representation. For this guy, if we take that fermionic group algebra, we get the Clifford algebra on one generator squaring 2 plus 1. And if now we have to pick a degree or pick a dimension, but let's say dimension 1, because that's the running example, and we compute the K-theory of that Clifford algebra, it will end up giving us the same Z as for the 10 versus the Myron chain earlier. On the interacting side, if we take that fermionic group, that's Z2x, 0, the tangential structure we get is pin minus. And in that dimension 1 plus 1 is 2. Dimension 2 for the invertible field theories, we get that Z mod 8 coming from the dimension 2 Fordism group here. And then there isn't a free contribution here. So this is how we see in the example how this symmetry is encoded compatibly. Let me look at the related example where we just look at the non-trivial second cohomology class as well. This will flip some signs around. So instead of Clifford plus 1, we get Clifford minus 1. And now the interesting dimension, one of the interesting dimensions to look at is in dimension 3. Again, we get a Z because secretly I want to start from Z in this talk always. And on the interacting side, we get pin plus structures instead of pin minus structures. So you could do a lot of other structures with this. Pin plus and pin minus are going to be the main examples for us in the rest of this talk, and we're going to kind of define a generalization of that. Okay, so but the important thing to take away is just that fermionic groups encode this well on both sides. On the free side, we're really going to be looking at Clifford algebra type symmetries in this talk. The interacting side will have something to do with pin plus and pin minus Fordism. Okay, so before I define the actual math, let me just remark about something we had to discuss with the symmetry type. So the choice of exactly which fermionic group to use is a little bit subtle. There could be multiple fermionic groups that kind of make sense for various classes. In addition to that, in studying the Bott spiral, there were also these primed classes. So half of the classes here have this prime, including the D prime. So let me just give an example of what this is supposed to be. So a primed phase, you're supposed to take 2 copies of a chiral phase. So for example, class D in 2 dimensions, and take opposite invariants. So normally when you stack these things, they would just cancel because they're inverses, but to prevent them from canceling, you instead add some additional symmetries. You enforce either a reflection or a spin conservation mod 2 symmetry and a time reversal symmetry to prevent them from canceling. And then you get this phase D prime, and more generally for the other types. And the thing about these primed phases is that on the free side, they're kind of indistinguishable from the unprimed phases, but they are important for making things work on the interacting side. So we had to figure out how to encode this with the fermionic groups. And because we added these 2 symmetries, one unitary, one anti-unitary, it seemed like a good idea to say, if we have some if we have some fermionic group GF that we're interested in and we want to form the primed version, let's add on one copy of the fermionic group corresponding to Clifford +1 and one copy corresponding to Clifford -1. Okay. Yes.
Case groups have a different symmetry.
Yes.
So therefore, they are distinguished by the TF. The TF have a one, then prime is another TF. So
Yes.
Yeah, if it's another TF, then the translation can be more like other things.
The classification will change.
We'll modify TF as taking all different.
So this is how I'm proposing to modify GF. I'm saying take the graded tensor product with these two pieces here, and we'll see if we'll change the interacting classification. Was that your question?
Yeah.
Okay, thanks very much. So we'll see here, if we use this definition of the prime, we want to see that the free phases actually look the same. And this follows because if we form that fermionic group algebra and plug it into K-theory, and we look at the prime thing ends up here having a tensor with Clifford 1, and Clifford 1, is Morita trivial. So the K-theory cannot see it. So K-theory cannot tell the difference between the group algebra on GF, the fermionic group algebra on GF and GF prime. But the interacting side certainly can, and that was very important for this application. So HGF was that tangential structure associated to your fermionic group. Then compare this with the primed version. These in general are not isomorphic, it's just a different tangential structure condition. So let me do an example where GF is just trivial. So like this kind of, we're just looking at spin bordism and then comparing it with the primed version thereof. And with these computations from Kaidi, Pera, Martinez, Tachikawa, and DeBrey, they were studying something called D-pin, but it happens to be isomorphic. You can look at these bordism groups and just see they totally don't match. So it's very important to know that, like, how many primes, or whether you're primed or unprimed when you're looking at the interacting side and you're trying to compute which phases there are. So for example, class D superconductor, we're not seeing these really big powers of 2 yet, but for the class D prime, we're seeing this C mod 8. The C mod 8 is related by dimensional reduction to the time reversal symmetric Majorana chain isomorphically, whereas there's a 0 if we were just looking at spin, if we were looking at the normal class D. Okay, am I supposed to stop at 8:50 or 8:55?
You can have about 10 minutes.
Okay, great. Thanks. So I talked a lot about symmetries, I talked a lot about primed phases, and now I want to finally say, okay, how are we comparing, how are we defining this map? How are we comparing K-theory with invertible field theories or K-theory with bordism? So following the approach of Fried-Hopkins, we're going to look at the Atiyah-Bott-Shapiro, or the spin orientation. So this will give me a map from spin bordism to K-theory. There's many different ways to phrase this, but one way is to say if I take a spin manifold M, I can form its spinor bundle, I can form the Dirac operator acting on sections thereof, and this will give me here a K homology class. I can also phrase it in terms of K-theory, not dualize. And so this will get me from spin bordism to K-theory. But we don't have spin bordism in all of our cases. We're not just looking at spin as the tangential structure. I talked about how we want to get all of these tangential structures associated to fermionic groups, which would be twisted versions thereof. And so to handle this, we're going to generalize the twisted Atiyah-Bott-Shapiro type maps that Fried-Hopkins defined for pin plus and pin minus. And so they also defined some other twisted ABS maps for other cases in the tenfold way. And it's surprising we actually couldn't use those. So we had to define ones that really looked closer to pin plus and pin minus. So let me say how we did that. So I'll just give the formula here. So let's look at an example. So class D prime. So class D is supposed to be spin. Class D prime is supposed to have this additional prime symmetry, these additional 2 symmetry generators. The tangential structure here is something that we call spin 1, It's isomorphic also to D-pin, if you are familiar with that. So it looks like spin bordism. where I have two Z2 twists, one by sigma, one by minus sigma. And so I want to use a Tiabat-Shapiro here, but I can't exactly use it because we're twisted. So the first thing we'll do is we'll modify the twist slightly. We'll get rid of sort of half the twist. The map we're going to use is SM sub sigma, the Smith homomorphism. And what this does is it cuts out a submanifold. So for sigma, it cuts out a submanifold whose normal bundle looks like a copy of sigma. And so you'll get a submanifold with a different tangential structure. Then you'll be left over with an extra Z2 bundle. We're just going to crush that, forget about it. And so now we're closer to being just spin. We can then take a Tiabat-Shapiro just parameterized over this Tom space VC2 sigma -1. And then to finally land in K-theory, we will use this difference bundle construction applied to sigma. And yeah, so if you were in the complex case and looking at a complex structure bundle, this difference bundle construction would give us like the Tom class, but here we're not, the bundle sigma isn't oriented, so we're not exactly doing a Tom isomorphism, but it's a similar construction. So with these two ingredients, basically the Smith homomorphism, taking that submanifold, and then using this particular K-theory class, these were used by Friedman-Hopkins in the pin plus and pin minus cases. We can now combine them to look at this 1,1 case. And we get a map now starting from twisted spin boardism up here, landing in K-theory. And we want to compute this. This is going to be our model. We'll call this ABS 1,1. Dualizing it will give us the free to interact map. And then actually we ended up having to do this not just for 1,1, but for L, K. These are spin manifolds where we twist by some number of line bundles. So we don't ask M to be spin, but we say you can add a bunch of line bundles and subtract a bunch of other line bundles and allow that to be a spin. That gives us another tangential structure. And then we can modify, we can basically just iterate our procedure to get a map that works for these things. And so for the L, K case, if L does not equal to K, then we actually don't land in the same degree, we change our degree. Okay. So now let me return to the computations that I started with. So once we had this ABS L, K defined, you can dualize it. That's getting us from some K-theory group to some invertible field theories with some twisted spin structures. We use some auxiliary maps to compute here, and then we use the atom spectral sequence, and we were able to compute this result here. So now you can see this K-theory group in dimension D with L many symmetries squaring to +1, K many symmetries with the opposite signature, landing in spin L, K invertible field theories. This is the computation we got. This is the result we got. And so this measures, reproduces what Krulewski and Stern found. We see that M tilde term, that's kind of measuring how many times we went around the box spiral. And so we get this multiplication by 16, which we really wanted to see. This is exciting. And let's see. Don't have too much time left, but let me just say a couple things, and if anyone's interested, we can discuss more later. But I mentioned that one of the subtleties in actually getting it to work, like the computation was great that it worked out, but it was very subtle setting things up so that it could be compatible with the dimensional reduction procedures of Krulewski and Stern. They really computed their examples via that approach, and we wanted to model that as well as just free interacting. So let's see. So half the time this dimensional reduction was an isomorphism, half the time it was multiplication by 2. If you go around by 8, that contributes to the multiplication by 16. To describe this, we knew Smith homomorphisms were related. So Hassan Komargowski-Thorngren noticed that Smith homomorphisms seem to be really related to this Bott spiral situation. And many other authors have also studied Smith homomorphisms and symmetry breaking. So we can look at a Smith homomorphism here. However, the claim is this doesn't quite work. We had to modify it. So in order to leave time for questions, let me just flash up on the screen. We defined 2 kinds of dimensional reduction maps. Each of them involves a Smith homomorphism. but it also involves a second step here. And yeah, so let's see what I should say here. So the first step for each of these maps is to take this submanifold. The second step also has physical interpretation here. But these are our maps that are sort of trying to go around the spiral instead of trying to go from the free side to the interacting side. And we wanted our free to interacting map to be compatible with these maps. And one thing we found was that in order to be compatible with this dimensional reduction, we couldn't, for example, take symmetry types used by Fried-Hopkins, for example, something like pin C tilde plus, pin C tilde minus, these kinds of things. We really had to use spin L comma K the whole way through. And these maps relating different L's and K's, different numbers of symmetries, we were able to show behaved as Krulewski and Stern had computed the isomorphism multiplication by 2. But in order to have these work, we needed that L comma K. So there's an example we ask about. Let me see. Yeah, so let me get to the end. If anyone has questions, we can go back, but I kind of said verbally, we really needed spin LK. We couldn't just use another fermionic group that kind of looked the same on the free side. We had to use this particular tangential structure. I didn't touch on the second 2 points here, but let me pause now for questions. So thanks very much for listening.
You made a passing remark that all the interactions you need are quartic. Is that something like one? Is that something you can see at all from your formalism? And if not, like what is the vibe?
No, I would love to know how to see that from the formalism. There must be some representation theory of spin, something like this. I'm really curious about what happens. Quartic terms won't always suffice outside of the tenfold way. There's some examples. But Krulewski and Stern showed that quartic terms. So they showed that quartic terms suffice by modifying the term that Fikowski-Kitaev came up like really explicitly. And I'd be super interested to know like if there's some kind of filtration on the order of terms that you're allowed to use to get your interacting classification, but I don't know. It's hard to see from the Bordism side.
Yeah, for the free fermion SPP, there's a periodic state increase minus by 8. So here, looking at for interacting fermion states, similar periodic state increase dimension by 8. The classification more or less the same, except some factor.
Yes, it's a factor of 16. And so Krulewski and Stern had observed that, and on the interacting side from this invertible field theory perspective, you can see that going around 8 times as dimensionally reducing our field theory on a bot manifold, so the 16-dimensional manifold. And so that reduction procedure gives us that multiplication by 16. So yeah.
But the spatial dimension increase by 8. Every time dimension increase by 8. The spatial dimension increase by 8.
Yes.
Then there is a classification similar.
Yes, the classification. Yeah, so again, it's not the entire classification. It's only the image of this free to interacting map. It's not seeing the intrinsically interacting faces, for example. But I have no reason to believe that the intrinsically interacting faces would also have like some interesting periodicity here. I think probably the image is the more interesting thing to look at. Yeah, but there's more there.
Do you think it's a spin L K the realization of spin C cells? It's very fast. What do you want and why some can fail this?
So I wouldn't say spin C because for spin LK we're trying to model only real symmetry types, real things. We can also look at like a primed version of spin C, but due to like periodicity there, the only things you'll get are spin C and pin C. Yeah, so yes, so hopefully I said real line bundle, but yes, spin LK is L. You can add L line bundles and you can subtract K many virtual bundles, and it's fine because we're looking at a stable tangential structure, so we're allowed to subtract bundles there because we only care about it being stable. Yeah, thanks for the question.
So talking a bit more about data two concepts you find.
Yeah, sure. So Okay, so these last two maps are the things in this diagram labeled SP, and then there's two types. SP stands for spiral. So these were running inverse to a dimensional reduction procedure, and they're supposed to model what Stern did. And we know that for dimensional reduction via some charged order parameter, the symmetry breaking Smith homomorphism story, we know Smith homomorphisms can be used for that. And so we thought, okay, let's try the Smith homomorphism, but this didn't have the right target for, it didn't land in the right type of symmetry here. For example, we had this extra Z2 factor, so we had to forget it. We actually had to define two different types, depending on this side. If we were trying to form a primed phase, we had to define this doubling map. And these two different maps work in different, each works half the time, and they have different behavior. So the left-hand side one is always an isomorphism on the relevant factors, and the right-hand side is always a multiplication by 2. So we were able to recover that.
All right, let's thank the speaker again.
It's Anton. He's going to give a blackboard to us. With the high resolution. After you get
Can I say that?
be careful. You're only one to have.
So Anton, I'll put up some sign. All right, let's get started with the second talk of today. We have Anton Kapustin to tell us about higher symmetry and homotopy theory.
Thank you for this quick. Yeah. Thank you for the opportunity. I'm going to be talking about the subject which I've been working on for a while, and there are some papers which are relevant, and I'll write them down. The archive number. So they're relevant, but they're not going to be they don't have all that much overlap with what's today's talk, because they're written before more general understanding which I developed over the last 2 months. So that's a more general scheme I'm going to discuss today. What's the issue? Well, Well, actually, before you start, so let me set the terminology. I'm going to be discussing how homotopy theory arises from quantum field theory or lattice model. So homotopy theory to produce a space.
Who gives the buttons?
It's the button
In the middle of the.
video, of course. No, never. So, yes. That one, that we don't want to get arrested is something for it. And the state, if they are here.
So homotopy theory, and then get some space Y, which is going to be classifying space. Space of all five symmetries. So so the fact that there is such a construction from here to here, is somehow an article of faith in the physics, in the quantum physics community, but there's no explanation how to get from here to there in general. Well, I guess it's what this would be for a particular Kapustin lattice model. And I'd like to explain how to get from here to there. And also, like, why do we want to get from here to there? Like, if you don't like homotopy theory, like, why borrow? Well, I want to explain why also you want to get there. And that's because there's another subject that are more familiar, it's anomalous. And you can sort of resolve anomalies of quantum field theory or lattice model, more such of a group axiom on quantum field theory or lattice model, if you know. So that's what I'd like to explain. So first of all, first I'm going to explain, why that's important, and then how I'll skip that. Now, but before we move on, let's set the terminology. So this Y is not really a space, even though it's for classifying space, but a homotopy type. And homotopy type is a topological space after equivalence. More specifically, in this talk, I'm going to be dealing with only with pointed connected homotopy type. Is all my spaces are distinguished pointed and well connected. So from now on, let's say it's homotopy type, I'm just going to point connected. So more specifically, what would like to explain? Well, I mean, so that reminds me of the lore, this lore, which tells you why we think like this. Well, we usually say that for quantum mechanics, as a symmetry group, and this group is like maybe some subgroup of the unitary group of the silver space, maybe a projected unitary group. And if you want, you can apply to the construction, which gives you classifying space of this group, which is space characterized by the fact that it's only a non-trivial homotopy group is type. It is F itself. So by definition, phi one of the is F. A lot of homotopy groups are trivial. So in other words, it's a one type. And not generally by n type, I mean homotopy type that such that all homotopy groups are starting higher than n just trivial. So that's well, of course, this actually is a functor. And in fact, you can commit trade talking about group theory, but for talking about one types, because it's actually equivalence of categories. But there's no payoff in quantum mechanics. There's no reason to think about one type at this point. But the law is, so you have T dimension to plus one, and G therefore is going to be a spatial dimension for one space. Maybe lattice model quantized model based on dimension D, then the standard thing. And this is, I would say, is believed, but for no really good, not no good reason, is that you can assign to it as a D plus one symmetry. D plus one. But it's actually easy to explain what this means by defining its classifying space. And the classifying space is so the classifying space is a D plus one type, and from now on, I'm just going to think when I say N group, I really mean the corresponding classifying space. So, okay, so that's what people think, and then how is it played in the previous thing? Well, supposedly, moreover, there's a called sign y, and supposedly phi one of y is what we call f, and it's called f naught. It's called 0 point symmetry. And it says that f supposedly, but more generally, phi equals 1y. I will have a group of p forms. But there's a lot more information in the homotopy type in general than just its homotopy groups. You cannot recover, the homotopy type y just by knowing homotopy groups. So why do we believe that? Well, these groups. Well, this is a general group. These are abelian groups for p greater than 1, for p greater than 0. Sorry. So that sort of matches because we think of physically of this as codimension. Well, in general, p-form symmetries correspond to topological invertible topological defects of codimension p. And in space. So that's the reason, if you think about space-time terms, this should be general group, while this is going to be abelian. However, as I said, there's a lot more information in the homotopy type, and that's not clear why this information, this mixing between different p-form symmetry groups should be encoded in the homotopy type. So that's the thing I would like to explain. But before I move on, I would just say that, okay, well, suppose you know this y. What can you do with it? Well, I claim that, I propose that you can actually, what's the most important thing it's good for is extracting Hooft anomalies, specifically Hooft anomalies of zero form symmetries. So here, a G action, well, it's an action of some abstract proof on my system. So what does it mean? So, well, normally it's like we have homomorphism from G to the group F, or not, same thing. This is first like now. So that's and the G action, and that's the G action on a quantum mechanical system. And then this classifying space construction being a function gives you also prefer just a map over classifying spaces. So this is a homomorphism, or this is a map, pointed map. So now, okay, so supposedly, given this, you should be able to extract something called Hooft anomaly. So how to extract that? So here's a proposal. So first of all, if you really believe that this is just E of phi 1 of y, then you think, well, okay, here's my y. So the canonical map here, I'm not going to explain why, but you have a map like this. You can ask whether it lifts to something, whether it can lift this map, that one, so this diagram can. So if you know what y is, you should be able to answer this. So as soon as you know this map, which you do because you know how G acts, you can figure out whether this map can be lifted to that using just purely homotopy theory. So, and this, I believe it should be thought of as a Hooft anomaly of the action. So if this is correct, then that sort of on one hand explains why I need to know why. On the other hand, reduces as anomalies just to think about higher symmetry. Yes.
Però it's an abstraction that exists.
Yes. Yes. So that's one way to think about it. Now, so to illustrate how this works, should work rather. Suppose I have so suppose it's G equals 1. So meaning I'm in two space-time dimensions, one spatial dimension. So here Y is a two group. And the two group, well, I think we're classifying space of two group. So it's just two type. So you can encode everything in terms of the following data. Great. So in this case,
Well, there also a homomorphism for how F0 acts on it.
yeah, in general, yes, but in this case, it turns out for the one we're talking about, it doesn't actually it acts trivially, so don't suppress that. So anyway, so yeah, the tuples which arise in this case actually have trivial action here. Yeah. So anyway, so okay, so this is this part that was called Y, and what the anomaly in this case, well, so this class called K-invariant precisely measures the failure of the space, which is the product of two things, namely, so kappa is a failure measures failure of Y, the product, simple product of the F0, F1. So not surprisingly, this abstraction I was talking about is just a fullback. So anomaly. Then leaves in a equal to fullback of the class. They were leaves in A3 of D F1. And okay, the only thing, okay, is it recognizable? Well, recognizable because actually, what's F1? If you think about what is the one form symmetrism over two-dimensional QFT? Well, there's one immediate obvious one, namely scalar unitaries. Just put a scalar number, C number, somewhere. Split topological and split invertible, so that's sort of a canonical, but almost trivial symmetry. It's trivial in terms of it doesn't act on anything. Just there to account for anomaly, basically. So in reality, this is just a 3 of G1. And it's well recognized in the work of Wapa on asymmetric orbitals that anomalies of 2D QFTs live in this. So that's a simple case, but only have one K invariant, only two non-trivial homomorphisms, but in general, with more complicated structure of anomalies because they have more complicated Y with several homomorphisms. Okay, now we know why we need to know what this homomorphic like Y is. Let's how do we how does the merge? Now I took the anomaly, so that's actually the relationship to anomaly is crucial. Because in a sense it says, well, to figure out what Y is, you need to think about what the anomalies are. The same thing, and those we know roughly as physicists. Those come from thinking about gauging symmetry. So let's discuss what it means to gauge symmetry. So we have again the situation. We have a G homomorphism from G to F, which is a zero form symmetry group. And so how do we gauge? What does it mean to gauge symmetry? Well, let's assume for the time being that G is actually a lead, even though it's not. I don't know if it's topology, but this is considered gauge in the case of G is a lead. Then people will say, well, you need to promote this min map which, well, you're living on some manifold. Again, not necessary in general, but with the manifold, and you don't promote this just Lie group G or sort of constant symmetries to of maps from continuous maps or smooth maps from X. And it's still going to impact somehow in the system, so it should embed the same path. So that's what this might say. Now this makes a lot of sense if G is connected. If it's not connected, suppose it's just infinite with the group of three or zero dimensional. But this, if it's X is also connected, then it doesn't make much sense because G then is the same as this one. The connected space mapping for disconnected group, there's no distinction. Creation seems trivial. So that's what people say, but it's not what they actually do. What do they do? So now another issue with this, by the way, is this. So when you say how to get a homomorphism, well, nothing ensures that this map cares about locality. So here is a well-defined notion of locality, some element of this group. Okay, it's we know what it means for it to say be identity outside some set. You would like, in some sense, this such elements to act also on this set of subset of space here. But just having homomorphism doesn't ensure that. The more structure we are taking into account. So what is the structure? But in reality, so this is like a role. But instead, it's supposed to default. So first of all, we need more structure. What is the structure? So we have first of all set of all open subsets of our manifold faucet, and we'd like to have the following. So we're going to have some function from this guys to some clues, and this function maps instead of so this is going to be our group of gauge information localized on living on subset tree. And this is going to be a group of symmetries of our system, which again is more localized. Now, what we really like to do is to say, well, okay, so the first one we have this, so there's more structure. You just don't have a single group like here. You have a whole collection of groups, and of course, if you just look at the whole thing, then that's what we call L. But in principle, there's a whole bunch of. And again, similarly here, not just single location information, but one for each focus zone. And what we'd like to do, so the structure, and also you have compatibility under compatibility under maps. Like if you have like U inside P, then you must have map from H of U to H of B. Actually, group homework. And it's similar here. And then of course, if you have like B which is inside W, then it should be compatible with that. So they can, let's say, then of course you can consider competition of these two maps or directly from here to there, do the same thing. Same thing. So what we're getting, well, it's not so a triple group. So this thing, we have a pair of triple, a pair of sheaves of 1 million. So that's what we really keep in the back of our mind when we talk about gauge. So the physical system must have some more structure than simply saying a group of symmetry on the physical space, or whatever that is. And in case of field theory, this is just you have just something still the regions are just open elements, open subsets. In some other systems, well, there's some more general fault, but some other fault that replaces the fault of open site. And explain to you after.
Well, that's H of space. H less.
Right. So what I just found H. H is going to replace this guy. and if group G is compact, is connected, you could do the natural choice for H. For example, you can try that. So you look at all elements in this group whose support, that is, set of a closure of the set of points where they're not identical, is inside. You can do that. However, that only works for G is compact, is a lead connected. It doesn't work on the other way. So I don't want to fix what H is. So let's get into the following picture. So the system is characterized by the security or ladder system. Next, we have some ricochet. Well, which is really the factor from often X groups. And when I say gauging, what do I mean? Well, we need to define ricochet H such that, and such that your absolute group G sits is a homomorph, is a subgroup of H of X. So H is the, H of X is the group of transformation which we don't care where they're localized, and I want constant gauge transformation inside there. I don't know what H of X is, but it's there. To find what and morphism of ricochets. Such that X is big to G, get that row. But by morphism just means the collection of maps like this. Homomorphism like this. So if I want to have a abstract transformation localized on U, map to abstract transformation localized, so to the non-abstract concrete transformation of a system localized in U. And of course, I want compatibility, with these maps. So these maps are called co-restriction maps. So it's like say, co-restriction map like this. So I want this diagram to put more morphism ricochets. So anyway, in particular, there is it's a component of this morphism at X of the whole space, and I want that to be a row when restricted. So it means to find some way from multi-symmetry to gauge them. So now the choice of this H is also part of gauging procedure. It's not fixed up right away. Now, so an abstraction to gauging this normally should be an abstraction to finding such a pair, ricochet and this F. Now, why is it a non-trivial problem? For example, if you why don't just say that H is F, and then take the little f to be just identity map. This maps everything identity. Well, it's if you could do that, that means that formulas just are never there. So the reason they're there is because you have some preconceived notion of what H of H should behave like the sort of gauge symmetry should behave. But your recursive F, which comes from the system, it's whatever it is, it might not satisfy some of this condition. So that's why you cannot just always take H to be F and get rid of it at all. Okay. So what are these preconceived notions that we want to impose. First of all, I want to bring some h of u in V must be generated by h of u and h of v. More precisely, okay, so let's have some say two regions, and I have some transformations of living on the U. I want any transformation here to be decomposable. The problem transformations here and there. More precisely, there's some maps from h of u here, from h of v to here, and I want the whole h of u and v to be just generating these two solids. That's what the one natural condition. It's sort of a multiplicative partition of unit. And transformation here should become all of transformations here and there. So, and second, no higher symmetry. That is, that's a more basic. You can explain what it is. My matter model what it is. The point is that I'm trying to gauge it zero probability. And F, the frequency F, might encodes also information about higher. So higher symmetries come from about thinking how you can localize ordinary symmetries. That's all that they are. So when I'm gauging a symmetry, I don't want to gauge higher symmetry. My H is not contained in closed higher symmetry. Well, F might. That's where another reason I don't know what it means. So okay, so what does it mean? The second condition.
What do you assume that they exceptions?
No, well, it's not then trivial. No, you don't need to assume anything. Just. So anyway, so how do we make sense of this condition? So you have a frequency of abelian groups, you can assign to it its homology. Now, so in here, well, sheaves have cohomology, co-sheaves have homology, yeah, well, also precosheaves, and we have check homology, for example. So I want to do something in an abelian case. That's what we like to do. Now that's that's not really possible to do. There's no reasonable way of doing this if F is just a precosheaf of groups. There's no analog of a check construction, say, which gives you something like check complex. Okay? So F must have extra structure, and it does have extra structure. So and what I mean by this homology, it's really homotopy type. So homology is going to be homotopy type. So that's the goal. We're going to describe some way of extracting homotopy type out of precosheaf with extra structure. And then I want to demand this homotopy type be very boring for H. Only have one form symmetries, only has zero form symmetries, but for F can something much more general. And that's why we can have two phenomena. Okay, so
What you described so far looks very much as something of package.
yeah. Yeah. Non-dynamical, yeah. Non-dynamic. Okay, so what's the extra structure? Okay, so first of all, how can you hope to get homotopy types? Well, to get a homotopy type, you don't need to have a topological space. Homotopy types arise in all kinds of other ways. For example, they arise combinatorially. as from some construction gadget called simplicial set. But that doesn't work for us because we want to construct not just homotopy type, but something sort of finite. Its homotopy groups will just stop at some point in terms of dimensional skills. Simplicial sets are not, don't really do that. So there's another, but there are other ways. So the homotopy types are very ubiquitous. So they're group theoretic constructions. In particular, there's some gadget called, for example, so remember the groups, right? So how to construct, how to get an n-type. Well, one way is to, like, if I want n is one, so from a group, construct and classify instead. We already know that. So the n equals 2 version is some gadget called cross module. Construct the two types. And more generally, if you want to construct n-type, there is a common generalization called the categorical, more generally, and have that and group get plus one type. You can get the more general plus one type. So now there's a nice reformulation. Like you can write this definition. I'm not going to write this definition; it takes too long. But there's a nice reformulation of this cat this Copetti construction. You can form it as an n cube of groups, n-dimensional cube of groups. You could edit this pattern. So they look at n equals 2, like the first non-trivial case, well, most non-trivial case. Just say you have 4 groups. One morphism between them. You have an action, well, it's commuting. Also, you have this guy acts on the other 3 by automorphisms. And then there is some strange map from like this, which says it has a whole long list of properties. So that's called this is called a cross square group, which is a cross chronicles. No, it gives you most general. Okay, so this Adam group is strict, but from which you can get a general n plus 1 type. Okay?
Are they B orders? B. Are they B? The N groups.
The subset groups. The abstract groups. Yeah, absolutely. So anyway, so this is like n plus 1 corresponds to cross module corresponds to. So this is your sort of cross one. This is your one cube of groups. 2 groups, homomorphic between them and some action of n on m. But here is a bit more structure, and there is more structure. Well, it is no more structure for higher dimensional cubes, but there is more condition. But then again, I'm not writing any conditions here. So this is more very suggestive because this suggests how to get this picture, suggests how to get a homotopy type by first constructing this n cube. And you can get it out of a precaution with special structure. What is special structure? I call it a cross precaution. So the point is this. So I'm saying the following. Suppose I have choose n regions in my space sitting inside some bigger region. This bigger region could be just the whole thing. So then I want to have extra structure, which does mean the following. I'm looking at the groups assigned to all intersections of this n guy. Then actually labeled by vertices of an n cube, right? So just take subset of set 0, 1 and just form this. So A can be any subset like this. So I get these groups, and I have maps. The map comes for free just because it's Prikashi. So I get an n cube, but you need also extra structure like that. And across Prikashi, precisely saying, well, I'm getting this extra structure. Right? This is my extra data across Prikashi. So if I have this guy, then I can do the following. I can have now a check structure. So I start with my system, which has a different cross Prikashi. I choose power of X, get across n cube, get an n cube with finite power. Cross n cube of group. And from that, by applying this construction of Lode and modified by Ellis and Steiner, I get a homomorphic. That's my homomorphic. That's a homomorphic. So now you can look at its properties, and it's not quite what I wanted to have. However, so I want to get some other one type of Y. So now the point is that actually this, whatever this guy is, the natural map from S to from running power is a map like that. That's because there's sort of a trivial cross cube where this point A is emphasized. You just put the f of x here and then trivial groups everywhere else. So this cross cube naturally maps to this cross. And therefore, you get the map from the classifying space of x to this. So if you inspect this, there's a natural candidate actually for the homomorphic type I'm up with Y. And this is a homomorphic fiber. This canonical. We can check that does have the right properties to serve as the type and complete suggestion or high performance in the domain. So this is a complete prescription, which depends though on the choice of the color. In this way, you get not just one homomorphic type, Z or Y, you get a whole sequence of them, one for each open color. The analog is a lattice system. So you can get also, the most of the power there. So it's not quite what we wanted, almost what we want. It's a sequence of homomorphic types. Ideally, we would like to say, well, if my cover nice, to be nice enough, actually nothing depends on just the power. And that's actually, I think, possible to prove in the lattice case that choose U to be made of cover of your space by polyhedral columns, then actually some of it doesn't depend on the cover. So it's a good column. So that's how we get what we're up to. And in this paper that I quoted in the beginning, so we implement this for P=1 and P=1 equals a slightly different setup, but we essentially extract the anomaly by constructing appropriate Y. To some particular power, we don't quite prove that not dependent on the power, subtle business, but very formal.
Namely, maybe I would expect that depending on the size that you should look at your system, you can have a symmetry of an edge or symmetry of its screen.
I'm looking at infinite volume from the start. And in fact, what is this Picker sheet F? So the key to construction say that what is the right Picker sheet F? Well, it depends. What I don't know. for one of lattice systems is a very natural candidate. And it's somewhat non-trivial to show that it has a, I mean, you could say that F of the lattice system, F of Q as circuits, finite depth circuits, approximately localized on rockets. Now, the subtlety here is that if U is unbounded, that's correct, but if U is bounded, then actually it's not quite correct. So it's this for the U unbounded. For U bounded, for Q is simply the unitary local observable. So this carries extra phase information, we will lose otherwise. So anyway, so that's my proposal for the cross Pikashev F is, and one can actually check that it's cross Pikashev of the structure if we well defined one.
All right, let's thank the speaker.
I don't understand the principle then.
Where?
Do you have a principle then?
This, yeah, no, not principle, just a vibrating sequence. So this is the,
I don't know. So I don't think of like the 25 that's with higher closer.
it's like this group, well, whatever. Okay, so it's just a, this is just a vibration sequence in the sense of one of the, so get along with the sequence.
Yeah. So
There's not even a big principle.
it's the definition of it looks a lot like that.
There's no principle. There's no principle. That what's vibration.
That's the this is it's not clear to me why it's size difference. It's not clear what's
It's so it's not. It's free because requiring quantity would be way too much. Even the simplest choices for this ligation are not bullshit on any reasonable sense. You just look at, say, my first example, just look at symmetry confirmation with the localizing that some functions from your manifold, from fancy group, which are supported in the security. They don't form a Cauchy loop. Why is it called? Well, because you don't restrict, you extend, right? Something localized in the region U, it's sometimes localized many bigger. So it's not both from F of U level during the test. You don't restrict.
so how do you get how do you get from this stuff? This localized
Yeah, there's no debundle. It still happens for me. Just mention it's really flat shape. Not topology. So my motivation that lattices they don't topology anyway until it's second order. Topology comes from there's not topology. It's homologous theory. It's not topology.
You can say that.
Well, in one dimension, we show in this paper that you reproduce Nayak-Else anomaly. And in fact, that's not, it's kind of built in. If you rethink what Nayak-Else did in homology first, this is what I have here. Yeah. So it's built in. For in two dimensions, of course, okay, so one thing to explain this thing is this recent work by Levin, Zhang, Calgary on anomalies of concentrability in two dimensions. There you have the two different anomalies. There's like, well, expected one degree 4 homology, also degree 2 class. And that both naturally comes from here. So I forgot to mention, turns out that actually it's not true. It's not true that by claimed before that pi this is true. So you're claiming that F0 is just my globally defined thing. Well, turns out actually that's not true. Only map like it. And it might be sort of the naive zero form symmetry. And this is a derived zero form symmetry. And this distinction is what leads to this degree 2 H2 index in two dimensions in the paper of Levin, Zhang, and there we go. Okay. So we get some extra. So it's actually not true that ordinary symmetry are just the same as by one of your homomorphic like this sometimes.
Can you get rid of the dependence of U covers?
Yeah, the
Get rid of the dependence of
yeah,
covers.
it's tricky business. Yeah, so I don't have a full proof, but yeah, it's not a trivial thing. So dependence on choice of cover, it is to reality, the construction. Why is it constant? Okay, so that requires, I think, maybe it's true in this setup, but I think there's a clean proof to stabilize in some sense. Namely, you lattice, we can put a lattice system. If you fix lattice systems, it's very hard to prove because I don't make it more than true that it's one lattice constant. But if you allow me to add sort of ancilla, additional point, stabilize, like in this recent work by Bowen Yang and Matty C. But I've also constructed something like that. Then to stabilize it, I'm going to show that it's stabilizing. So on the system, then you do get independent choice of cover if the cover is nice.
Nice meant just cones off to infinity. Like
Right?
nice meant that there only opens or cones. So
Yeah, the polyhedral cones. Or I just know
you're really just living at infinity. You've got the polygons at infinity and you pull them into
Right.
cones.
Yeah. So the point is that Bowen and Matty show that any QCA on a cone is actually a circuit. If you know that, then you can stabilize the property. If you know that, you can show that it exists independent of the circuit.
Do you have any explanation about that operation of these rules, like
Sorry?
right-hand bracket?
Can you speak up, please?
Do you have any explanation of the right-hand bracket, that operation?
Oh, sure. Yeah, you can extract all this stuff. No, and physically, this is just this. You have to defect two, say, in dimension 3. You have like a bracket from, pi 2 to pi 3, right? This is just this picture. You have two dimension to defect, which are linked. So you can get it from, of course, from also this cross squared.
There are many phenomena that arise from ideosynthesis mixed. This is only about field.
So I'm talking about anomalies for zero form symmetries. They arise from mixing between zero form symmetries and higher forms. Like us, what are about anomalies of higher form symmetries? Can define them through within the form. Yeah, the second paper with less linear way to explain a little bit.
All right, let's thank Anton again.
Basically, like to deal with solid.
Comunque sto malissimo, perciò faccio da seminario.
Vuoi che ti facciamo sventolare da un PhD student?
No, stavo chissando io posso fare questo mio.
Vuoi cambiare?
Non so, sono un po' così, c'è tipo 50% di possibilità che venga a metà del coso.
Well, I haven't heard about this, so then of course, can't define can groups where collaborative either the ecology, then of course you can you have more superficial direct models. You can just like the superficial direct diagonal. Where's
Like Copetti. For example, we have a tube symmetry, and then we can use various properties. But then from the quotient perspective, this is the perspective. There are some equivalents between them when you do the actual physical matter. From the pre-quotient perspective, how do we get tough models from the same two groups are actually
Let's get started. Christian, you need the mic. Laser pointer at the top. Show the potential. Everybody goes to sleep. Okay. All right. So let's get started with the last talk of the morning session. We're very happy to have Christian here to tell us about when symmetries twist, anomaly inflow on monodromy defects.
Okay, thank you very much for the invitation. I'm going to try to do my best. I think I'm like halfway, it's a bit full for me, so I'm going to try to get to the talk. If you see me going down. And but I also apologize, I wanted to put more references in the talk yesterday, but it was too hot for me. I just managed to do this. I hope this is some solace. I thought that I'm going to take a bath in this nice pool and so on. So let me see if I can move the mouse from the middle here. Maybe. Okay, so just to give some motivation, well, symmetries are powerful, and this we all know. They have a very rich but rigid mathematical structure. They give selection rule on dynamical processes like correlation functions, scattering amplitudes, and so on. And they give exact constraint large flows for this is like my motivation to study. But this talk will be about defects. Defects are extended impurities which appear everywhere from air to physics, like strings and Wilson lines, to lattice impurities, and they probe from a couple bulk observables like confinement, topological order, and so on. However, they're quite hard to study because often they lie outside perturbative control, like apart from some special points like large N, SUSY, and theories. And there are many works dealing with this type of perturbative expansion. But if you want to really understand defects, new tools are needed. It could be like Bootstrap, which has a long history in trying to understand properties of defect, or new methods such as fuzzy sphere. In this talk, I will talk about how categorical symmetries or symmetries in general give you some handle in describing the dynamics of the. So the important point here is that symmetries act on defect. This is quite obvious and was realized very early on in the subject. But what wasn't realized completely in the beginning is that the action on symmetry on an extended defect hides a lot of higher algebraic structure. I think probably the first place, maybe it's when people talked about symmetry fractionalization on the lattice, but then there were many works in the context of categorical symmetry about how this higher structure appears in a study. And this type of representations give you new handles in the properties of defects. For example, by studying the realization of Stokes anomalies on defects. And another very nice way to study defects is to study defects with braided symmetries of the bulk. These are kind of families of boundary condition of defects, which have been studied in several works, and how the bulk symmetry implies properties for their physical structure. And you can think of this as some type of fluke, in which on one side you have symmetries, on the other you have central defects. And you can use symmetries to constrain and maintain the behavior of defects. On the other hand, you can use defects to probe and characterize how symmetries are realized in the bulk. So in this talk, I will talk about a special type of defects, which is monodromy defect. And this implication will be using DMS probing disordered phases of matter. This is something well known in condensed matter. And the other arrow will be to use anomaly flow to predict the protected feature of these defects in gaseous phases. Okay, so just to give you some motivation, you can think about how you would probe spontaneous symmetry breaking of an ordinary symmetry. Like, for example, here we have a spin on the lattice. Yes, so using defects. Usually you would compute correlation functions at different points and take some limit to extending the series as SSP phase. But you can also think of inserting a heavy probe at some point on the lattice into this heavy red line in my picture. And this defines with some coupling, this coupling is called H here, and defines some heavy defects in the lattice system. And this is called the pinning field defect. And you can think of detecting the symmetry breaking phase instead of talking about correlation function of local operators far away. You can talk about the free energy of this defect as a function of H. The same ordered phase, it gets maximized or minimized depending on your sign convention when it's aligned with the magnetic field. And if you're in a disordered phase, it's independent of the direction of H. Okay. Then you can ask, how can I probe disorder? So if you have a disordered phase, so it has no local order parameters, such as an SPT, can I also probe this with defects? And the natural way is to use what's called a monodromy defect, or string order parameter. So you consider, here it's like a lattice system, I consider a bulk symmetry defect, which is called S in this slide, and they terminate at some point in the lattice. And this is extended through time, which is the vertical direction. And what will happen in general is that while the bulk system is disordered, so you don't have a local parameter there, the physics on the defect that can be ordered. So you can have a local order parameter. Or this can be gapless. So in this way, you can think of probing the SPT degrees of freedom by the degrees of freedom living on the defect, instead of using, for example, boundary condition. And the way this works is a variation of the decorated domain wall construction that I will briefly review now. This is kind of the main actor of this story, monodromy. So how does this work? So for this talk, we will consider the zero-point symmetry. G is a group. And this is D for me is D plus 1 is the space-time dimension, this setup. And I am in some SPT, and you know that's big omega. So if I insert the symmetry defect now, UG, in this phase, the phase still remains trivial. That's what an SPT is. But it can be dressed, but the defect for volume can be dressed by a lower dimensional SPT. This is why this is the corrector. The system at this point is still gapped and is still disordered everywhere, so you cannot find the local order parameter. And to compute the correction, you perform a twisted compactification in high energy language. So you take a flat gauge background with a circle, you put a velocity g on the circle. When you compactify, the SPT action gives you the action tau of the SPT that's being stuck on UG. This is a procedure you can carry out explicitly. If you work with all this group, there's some push-forward operation that does the same thing. So it's like a well-defined operation. This tau can also be trivial. So in that case, you have to be very careful about the trivialization. So what's the punchline then? Now you consider an open symmetry defect in this setting. And you see, because of the dressing, the monodromy defect, which here is called T of G, must carry edge modes for this tau G SPT. So if you have a non-trivial tau G, given by this wrestling, you have three options. Either this monodromy defect spontaneously break the symmetry. Here, G is the centralizer of G, the symmetry that remains once you put the symmetry defect, but you should just think of it as G for most of the examples. So either you break the symmetry, that's what usually happens at the boundary of an SPT. So what happens then is that the bulk system is ordered, but the defect, the bulk system is disordered, but the defect is ordered. Second, there can be anomalies that can be separated by topological order, so without symmetry breaking. In this setting, this would require this d plus 1, not d bigger than 5. But what did I put there? No, yeah, because the TG is quite small dimensional. And this leads you to some symmetry extension on this defect, which is a bit of a different process. And the third, more radical option is that this monodromy defect is gapless in a gap phase of map. Okay. So let me give you some simple examples. I mean, if there are any questions, this is also a good time for questions.
Do you think that symmetry of the SPT is the same, like about the convention structure, or can you allow the question like this means
No, it's not the same. You have to be careful about what consensus structure is there.
I think it means with space.
Yeah. Also, this defect has some rotation symmetry around it. This also mixes with the internal symmetry. I'm just looking at a simple situation in which everything is internal. Then at most what can happen is that the symmetry realized on the defect is some extension. It can be a like higher group also, but it's some symmetry extension. Okay. So it's very simple example is you can start with type 3 SPT in plus 1D. And you can compute this transgression, this reduction in a C background, and you get the usual Z2 times Z2 SPT in 1 plus 1D. This is the tau that leaves. This is really hard to use. Okay, well, there's a tau in this slide. And now you can talk about how you terminate this structure. And of course, there is no symmetric boundary condition for the 1 plus 1D SPT. So the edge modes on this DC will break the remaining Z2 times Z2 symmetry. And you have an ordered phase with 2 vacua on the monodromy. So in the bulk system is ordered, but it is ordered by its SPT. And on the monodromy defect, you find a one-dimensional ordered phase. This is like what happens. Another less trivial example is you can take integer quantable state, just looking here at the forest source, so just a Chern-Simons term with level 1. And you also compute the same transgression and this theta angle. We say trivial SPT in 2D, but you cannot trivialize it in a strictly U1 preserving manner. What you would like to do is to write this type of Wilson line, which is just this total derivative will be tau of theta. But as you see, this is ill quantized because theta is not 2 pi times an e. So you cannot quite do it. But the solution here is very simple. You just state that the symmetry is extended on the monodromy defect in such a way that this theta over 2 pi becomes a well-defined coefficient for the Wilson line. And there are two cases. If theta is 2 pi p over n, it's n-fold cover of U1, which is still U1, but it is through this central n-fold cover. And otherwise, it's just non-compact symmetry R. Okay. And furthermore, because of this continuous symmetry as a non-trivial pi 1, there is an anomaly in the space of defect couplings, which means that if I adiabatically change theta to theta plus 2 pi, I get a non-trivial effect on this monodromy defect T of theta, which in this case is the stacking of the integer Charles Wilson line. This means that in the Hilbert space, which is the Hilbert space of this defect here, in the Hilbert space, I have found 1 unit of charge. This is essentially Paul's bound from the bulk anomaly. So if you And this type of spectral flow is matched by what happens at theta equal to pi, because at theta equal to pi, the tau of theta is non-trivial SPT for E1 times charge conjugation, if you want. And this T of pi sometimes breaks C, and that's the usual case of a spectral flow, in which you start from one vacuum. Once you go to the midpoint of the circle, two vapor go inside, and you have spontaneity break. I don't know. Question like this. This is the vacuum with zero charge, goes to one charge. This one charge goes to zero charge. Here this is equal to pi, which works. Like this is kind of the picture for this very simple integer quantity. Okay, so let's get to the second part of the talk, if there are no questions. So you can now think of using this in the other direction. So I told you the first direction was to use the monodromy defect to probe the bulk symmetry, but you can also do it the other way around. And you can try now to use the bulk anomaly to understand the physics on the monodromy. And the way you do it is just realizing the system, gapless system, as the boundary modes of the bulk symmetry. Maybe I will draw this picture again here on the blackboard. Enough. The case. So what you will do very naively, here you have your gapless modes, here you have your SPT omega, and a symmetry defect in the gapless space is just some symmetry defect which extends to the bulk omega. Here it's an invertible phase, so this acts trivially on everything, but here it does not. No, so there are no colors. This already right because guy will be the defect in the gapless space. And as I told you, this would be a BUG times tau of G. This will be decorated. So you can think now of taking this full part here and moving it down this way onto the boundary. So on the boundary, this is a USP. The theory gets stuck to this SPT tau G. It's just this big defect which I moved this way. No, UG is part at free very here, but stacks SPT. So the important point is that in the presence of the anomaly, the symmetry defect of the gapless theory is not quite a defect, but it's more like a domain one between the theory and the theory stack SPT, which is not particularly impactful usually, but is impactful if I want to study the monodromy defect. So if I want now to study the monodromy defect, I have to terminate this object at a space-time dimension 2 perfect. This is a point here. But as you see, I cannot just go from here to here continuously because these are two different gapless SPTs. And the way around it is that I have to add a topological domain wall here if I want to preserve the rotation symmetry at this point, which also gives us the edge modes of tau G. This was what I called PG. So I would argue this is the correct construction of the monodromy defect in the case of the anomalous symmetry. And people study this type of defect in the past, and they study the defect Hilbert space. And if you look at the defect Hilbert space, you see some degeneracy, which are just the states of the TFT, essentially. And if you want, the 3D picture is the one on the slide. No, this MG is the monodromy defect, but now it's kind of a domain wall between the symmetry defect UG and some TQFT. So the properties I told you before of this TFT translating properties of the monodromy defect. So the first is if T of G spontaneously breaks a symmetry, so these were just the edge modes of the tau G, then the monodromy defect is non-simple. This means that just that it's the direct sum of many defects, and each defect corresponds to a vacuum of this theory. For example, if you break charge conjugation, you have two vacua here, and this corresponds to the fact that these guys are sum of two. Or you can just take a single guy and it will break the similar pattern. The second, if it's topologically ordered, this MG will carry some protected modes which come from the edge of topological order. And the third case is that when T of G is gapless, so it was not possible to find a gap domain wall between this SPT and figure one, then the monodromy defect is not quite well defined because it would like to impose this rotational symmetry around this point. But of course, if this domain wall is gapless, you can't really rotate it. And the monodromy defect as such does not exist. Of course, you can define this type of domain wall construction, which is well-defined object, but that's the best you can do. Okay. So, okay, maybe let me give you an example, which is a very simple one, the one of the chiral fermion. So we just consider 3+1D Dirac fermion. Again, this is just a free theory, that's the action. And as you very well know, it has two symmetries, a vector and the axial symmetry, which act in that way on the fermionic field. This has a perturbative anomaly. This is like the perturbative part, is the only part I will look at in this example, which is essentially the U1 V times 1A anomaly times the gravitational part. And I just put between the square brackets the part that encores the spin C structure. Just because this you need a spin C structure to define this theory. It is important in some computations, but will not be very important in the example. Right? And now once I the monodromy defect for this anomalous symmetry, this just means that as the fermion goes around this surface, this is 3+1B, which is a 2D surface. This is actually as the fermion goes around, so psi of theta plus 2 pi, if theta is plus 2 pi is just the angle on here, it's just the axial rotation. Because these twist to boundary conditions, you can think of it as a background field, background flux for the axial symmetry. This is just the setup. You can compute this transgression. This tau theta is also a trivial SPT, the similar case as the U1 case I had before. It's just a 3+1B theta angle, no? Again, this is a trivial SPT, but you cannot really trivialize it in a U1 preserving way. So there are two things you can do. First, you just keep the fractional response. So the SPT works like this. And if I just try to trivialize this, I get Christian-Simon's term, but with a fractional level. So first, I can just keep the fractional response. This is okay because these are gapless modes, so they can have fractional response. But this leads to the fact that the vector symmetry is fractionalized on the twist-table space. And to see the fractionalization, you have to put a monopole background. And in that case, the space carries fractional charges. Or if you want to think of this symmetry as some weakly gauge symmetry, like the vector symmetry of 3D, then you should actually get rid of the fractional response. And the way you do it is by stacking a fractional quantum Hall state. This was explored some years ago in the context of non-invertible symmetries. And this is a bit of a choice of defect you want to work with. In the field theory, both are fine defects, and you can choose which one to talk about. And when theta over 2 pi is a fractional number, then you can just stack some fractional quantum Hall state with some Hall conductance and get rid of the gravitational part by some decoupled theory. And you have some canonical candidate for what is the part which couples to the U1 symmetry, which is this minimal theory of Sinlan and Seiberg. This is like the construction in the case of the free fermion. But what I think is interesting is that you still have this type of spectral pump, which is independent of how you choose to define the defect microscopically. So again, the group has a pi1, so you can detect a pi1 on the modular defect. So what you can try to understand is I start from m of 0. This is just inner defect. And then adiabatically, I turn on a 2 pi flux, which is also a trigger symmetry defect. And I look at what happens. So if you start from your transaction formula, you see that this type of object pumps integer quantum Mole state. This is gravitational part, so the whole conductance is 1, and it's minus. It's 1 for the for this case. I believe it's 2. I think it's 1. Okay. And so what happens if you adiabatically perform this process? If I do it adiabatically, you will pump the edge mode of this integer quantum Mole state on the M2 pi. So this will post a chiral chiral mode. And it's the signature of the bonding in the bond. And the way you can see it is that you can actually compute something for this defect, which is called the B function. So the B function is just the coefficient of the Weyl anomaly on the defect. So if I take Weyl transformation of the defect effective action, the CFP will be 24 pi times this is just the Weyl anomaly on the defect. This has been computed in some older work for the vector symmetry. You can do it for the axial symmetry essentially, and has this fun form. So what I want to notice is that this function is not periodic in theta, and actually b of 2 pi minus b of 0 is 1. So this type of Weyl anomaly changes once you go around the circle for the modular defect. And if you want to compute the central charges of the edge modes, which I predict, what we have to also subtract or sum are the pure gravitational anomalies that you are pumping, which come here. So the correct computation is that the C left, the left central charge is D plus kg over 2, and kg is the coefficient of this term here, and delta. And delta C right, delta B minus delta. So now if you do the computation correctly, there was a 2, this was the Weyl segment, the Dirac as a factor of 2. If the computation correctly, this comes out to be 0, and this comes out to be 2. And these are the same chiral modes you predict from the anomaly. And you can also do a computation just using the modes of the fermion in this axial background, which I didn't put for lack of time. And you see the same thing. There is a decoupled chiral mode which goes down and becomes non-normalizable underneath. Okay, so this is more or less what I have to say. It's just a way to see the bulk anomaly from the modeling defect. And to summarize what happens in this case, is very similar to the U1 case I gave you before. So again, there's this non-trivial pump associated with pi 1 of U1. If you are at theta equal to pi, the defect breaks the charge conjugation or time reversal symmetry that's present there. And you can check it in the explicit utilization of the Dirac. So at pi you have to vacua. The defect is non-simple. At rational points where theta is 2 pi over n, you have extension to a cover of U1, or you can have some fractional quantum pole modes to cancel it. And when pi, you don't have this fractional value, you have to extend the symmetry to R. So it's very similar. And once you go around the circle adiabatically, you pump the edge modes of the integer quantum Mole state on the node. So something I thought it's quite funny, don't really know what to make about it, is that at theta equal to pi, you have the plus one dimensional time-reversing invariant topological insulator, which also has Gauss boundary conditions which do not break Gauss conjugation, for example, the T-Packen. So one could, in principle, choose this in this kind of diagram, T-Pi, identified with the T-Packen, and then there should be no need for symmetry breaking at theta equal to pi. In the free fermion case, this doesn't happen. So if you try to do it, there will be an RG flow and it will still flow to the symmetry breaking boundary condition. But I think it's funny to think about this type of interfaces between topological orders and Douglas anomalous theories, and whether they have something new to say about how symmetry is preserved or realized on boundaries. Okay, so this is more or less what I had to say, which is good, like this was short, So some open question. So here we consider the pi one. Of course, we have also iron of multiple groups of G. There should be some type of higher spectral pumps. I think for boundary conditions, these are understood, but for the modern G effect, these are not understood. And one can consider non-invertible symmetries instead of invertible ones. There is some work with duality defects by Schwang and other people the last year, which find some chiral edge modes from this defect, which are essentially come from the top anomaly if you have the simply ungate. Another nice application, I think, from more applied computation is what happens to Rényi or conical defects, because these are what you use to compute entanglement entropy. And if you have gravitational anomaly, these look a lot like a monodromy defect, but for the gravitational connection. So there might be some interesting predictions for the corner entanglement entropy, these defects. Another more condensed matter thing is what happens to crystalline defects, so like this discrimination, dislocation of the lattice. Because in this case, you can have actually gapless monodromy defects in gap phases. Just need to choose the phase in the correct way. And this has been already seen in previous studies. I just want to see if this can be formalized completely. And the last point, which is maybe connected to a talk of tomorrow, is what happens if we try to probe the monodromy defect via scattering experiments. So you can try to take the bulk fermions and scatter them on the monodromy defect. And I'm curious whether you can use scattering amplitudes to probe this topological data in a similar way in which you can probe some non-trivial topological data on magnetic monopoles by scattering. Okay, so this is all, and thank you very much.
Questions? Maybe I'll start. Can you go back to the previous slide?
Yes.
I just wonder if you could elaborate on the first bullet point of higher spectral pumps and what you've been thinking about that.
Yeah, I mean, the point would be, so here I told you what detects the pi one, Pi one of G, you can have like some type of Taurus pump. In the gapless setting, you're pumping gapless headphones. If you have higher spectral pumps, higher pies, you have to perform pumps in higher dimension. So the way it works on the boundary is Brandon told me this, so I'm just repeating, is that you can have some, for example, local operators like fermions that are present on the boundary and encode the higher monodromy groups. But there is no complete theory of this. So I think it's interesting to see what happens if you have soft anomalies, for example, for non-abelian group, and see whether you can detect this with these higher spectral pumps and not just the abelian pump.
Is it related to defect anomalies in the space of couplings that are not just one cycle, but from higher cycles?
Exactly. Yeah. That's the way to think about it.
What about the role of
The role of what?
optical?
Postnikov. Not that in the comments. I don't know, what do you want to know precisely?
Actually, just you had an example.
No, about the defect in space, no, in the space of coupling, so we'll start.
Yeah.
Okay, so, but I mean, the only thing I can tell you is that sometimes you have some non-trivial extension to higher groups in these cases, but I don't know what to say about the anomaly space of coupling.
So there is a interesting work that we have put together about the linear structure of the galaxy and the regulatory effect of that in the galaxy and then we constructed that ISO X images for these higher structures can those guys to further more effects and like you thought about what would be the endpoints and goals.
Those TKPs are related to this construction in the sense that those are ways in which in the ungated theory you compress the symmetry defects to cancel the result of anomaly. And yeah, you can suggest most in say higher form symmetry. So you can take model defect. It's a very similar construction. I think I mean the main problem is that the most discrete symmetry is what you will find is just that the symmetry is broken on the model defect, so it's not a simple defect. So it's there are some of many parts.
Yes,
but this is interesting if you want to probe like STT, so because anyone can think of this as the phase in order, just this co-dimension two locus, but disordered away from this, which is maybe a more effective way. But this is something very well known from the smart, I think. Just that the energy language that people didn't think about. This is my impression.
All right, if there are no more questions, let's thank Christian.
Yeah. It's actually related to the ones that So I want to model the so it's just that last way, of course. So there are some beautiful phenomena. This case, it's small. You have to go careful. It's not very nice. You have inverse cast. So but then you are refining a bit because we talk about quantity. That's a key off there. That is. The bottom works out. It generates an extension. But if it's certainly for you,